molecular system, and this is a very difficult problem, a very difficult many-body problem, adding on top of a difficult many-body problem. This is just part of an ongoing collaboration that I've had with Carlos Silva for years and years, going back to even when I was we did a Fulbright in Canada talking about some of the ideas of how we can start using quantum condensates and et cetera. And also with Andrei Pirotinsky at Los Alamos, we've had lots of work looking at quantum phase transitions in nanorods and driven open quantum systems. And anyway, so these are sort of the pieces of the pie, if you wish. And I think the shot across the bow, at least in terms of the US in interest in quantum light and quantum spectroscopy and sort of precipitating in this National Quantum Initiative, was this really interesting paper that came out in Science 2017 where the Chinese were able to bounce entangled photons, or bounce a photon, part of an entangled pair of a photon from a satellite and transmit information quantum mechanically from one city to another city. And this is highly desired for secure communications and communication channels. And I mentioned this at a meeting a couple years ago, and I think it was Laura Hertz at Oxford said, yeah, this is probably of mostly interest by drug lords, terrorists, El Chapo, and Donald Trump, so you can send secure tweets. But maybe Donald Trump really isn't so interested in secure tweets. But anyway, but our goal in a lot of this is to think about, if I have a molecular system in a cavity and I put in an input state, and I think of this molecular system as simply a unitary transformation that does something to the quantum state of the photon. You can formulate all of this in the same language as you would as a quantum logic gate, where you would have a control bit in the upper block of this 2x2 matrix, and then a manipulated bit in the bottom. And ultimately, we'd like to be able to string molecular systems together. Maybe this is like one of the things we could do. Maybe build it together as a way that one can take a quantum entangled photon source, manipulate the quantum photon source, and look at photons in coincidence as a means of doing quantum computation. And again, the scalability and everything else is difficult to deal with this. And of course, one of the things with molecular systems, you want to do this at finite temperature, which is an issue that we also have to deal with. So we have to deal with the fact that these are systems that undergo decoherence, undergo dephasing, undergo different kind of things like that. And for our work, we were inspired by a paper that was in Scientific Reports in 2017. It's a paper by Kalashnikov and Kravitsky et al. And it's a really interesting paper. In the abstract, what caught my eye in the abstract was, it is probably difficult to read. It's even difficult to read here. It says that exploiting quantum interference of entangled photons, it's possible to measure the dephasing time of a resonant media on the femtosecond timescale down to 100 femtoseconds using accessible continuous wave laser and single photon counting with a technique that's called the Hangon Mendel interferometry. And as, again, somebody who likes to talk to ultra-fast spectroscopists and think about ultra-fast processes in molecular systems, being able to measure a 100 femtosecond timescale process, even though it's basically the homogeneous line shape of a quantum emitter, with CW ordinary off-the-shelf laser sources. Now, granted, a Hangon Mendel interferometry setup is about $90,000 or so, but being able to achieve 100 femtoseconds with a $100,000 apparatus is intriguing. And then there was another paper that I noticed in Scientific Reports about a year earlier than this, and again has this sort of beautiful statement in it that says that the entanglement spectrum, if I can look at some spectrum that like, for example, the entropy contains useful and non-trivial information concerning the many-body correlations in a condensed phase systems. And so this really sort of set the stage for us thinking about, well, how can we use quantum entangled photons to really dig out and pull out these many-body correlations. So let's think about this in terms of a bipartite system. Maybe the photons are A and the system is B that I'm interested in. And if the system is separable, or maybe even if I have two subsystems within the same block, if the two subsystems are really separable, then there is no entanglement between the two. And so we've heard about this idea of entanglement growth due to correlations between the different subsystems. And if you have correlations between the subsystems, you start getting entanglements, and it's this sort of the measure, the entanglement is really a measurement of how interacting the two different subsystems are, how many correlations, how many contacts do I have between the subsystems. You can quantify this in different sort of mathematical ways. You have the Renyi entropy, you can quantify this as a purity, and the sufficient condition for entanglement is that the entropy of the subsystem is bigger than the entropy of the whole system, and likewise with A and B. And you can also show that if A and B are members of the same pure state, that the entropy of A and the entropy of B are necessarily the same. And that's an interesting thing to think about. Again, we've heard about entropy and in different contexts today. What we want to look at in terms of a spectroscopy, so that can I look at changes in the entropy as a correlation or as a measure of many-body interactions within the medium. So if I have an incoming Fock state of photons and I look at the entropy of that state, and I look at the outgoing wave function of photons, and I look at the entropy of that state, changes in that entropy should give me changes in that entanglement should give me a direct measure of the interactions going on within the systems. If there's no interactions going on with the system, one photon sees the system, another photon interacts with the system, and they never talk to each other via the medium. But maybe it's possible for a photon to go in, another photon that's a member of the same Fock state, and interacting with each other through the medium, which is what happens in a polariton system, and they go out carrying forward that interaction. And basically, you can show again that if I write out the scattering matrix or the transformation between the input to the output state that I would have, for example, maybe F is the input amplitude. If I can always write this the amplitude, this transformation as in the following way, it's following decomposable way, as a product of an amplitude for one particle scattering, an amplitude for the other particle scattering, then an irreducible term that I'm going to write is some sort of summation, like for example, like this. And you can perform Schmidt decomposition. You can show that the entropy must always change because of the interactions that would be carried through this non-reducible form. Okay, so what I wanted to be able to do then is to come up with a physical theory for this irreducible form. Now, and being in the UK presently, we deal with this issue of irreducibility and separability very much up front on a daily basis, because as the EU is, England is trying to divorce itself from the EU, maybe forming a state like this, we have to deal with the fact that maybe people want to cross the border and go back and forth between England and Ireland, or in my case, going back to the United Kingdom. But also in the United States, we deal with this in the following way. We have one set of actors, another set of actors, and cross-correlators going on in between. Of course, according to the Mueller report, there is, well, no collusion, but that's not probably quite true, because all of this is going on under the watchful eye of Robert Mueller. He just has the most beautiful eyes, I think. And anyway, so yes. Okay, so in the Hangon-Mendel experiment, this Kalashnikov experiment, I love this analogy. So in the Hangon-Mendel experiment, what we want to be able to do is imagine we put a system here in one arm of the Hangon-Mendel interferometer. Now, the way the Hangon-Mendel experiment works is you create an entanglement. In this case, we'll have the Trump photon and the Putin photon. One goes one way, one goes the other way, and of course you don't know which one goes up and which one goes down because they're entangled. And you allow a movable mirror to adjust really the path length of one of the upper arm photon relative to that of the lower photon. And if I take out the sample, S, you can bring these two photons back together in a beam splitter, recombine, and look at coincidence. And it's really easy to show a basic, again, looking at the beam splitter as a unitary transformation, that if the two path lengths are the same, you get a zero in between, and you get this what's called a Hangon-Mendel dip. And what we wanted to do is to say, well, let's imagine that one of the photons, maybe the Vladimir Putin photon, goes through the sample, picks up some sort of interaction with the sample, And then when it's recombined with a Trump photon, and I go back to, and Robert Mueller measures all of this, do I still see evidence of the entanglement? What has changed? What is different? And what can I then correlate what's going on within the system? Or can I correlate dynamics in the system to this entanglement spectrum? So the way the Hangon-Mendel interferometry works, this is a simple pictorial way to look at it. If you have two photons of the same color going through the beam splitter, you get a negative sign for the case where one photon goes up and one photon goes down. And so that cancels exactly if the two photons coming into the beam splitter are identical. And then the non-coincident terms correspond to, you get an additive term. So, but, you know, in doing an experiment, you can throw that away because the only thing that I want to look at is when I have two coincident counts within a given threshold time at the coincidence counters. And this is a really beautiful experiment from Hangon-Mendel, 1989 experiment, which really showed, you know, this idea that you can look at photon coincidence and that there is this quantum mechanical entanglement between photons. And this is, again, a picture from the Kalashnikov experiment. This is also a Kalashnikov car, by the way. If you have no sample in the beam arm, you do in fact get this Hangon-Mendel dip, which is this zero at zero time delay. The wiggles are simply the aperture function. This is just the photon amplitude coming out of the SPDC. It's just a Fresnel aperture. And then if you put a sample in the pathway, you get a shift. Everything is shifted over to positive times. Everything at negative time is a little bit of ringing from the original aperture. But all of this change is exactly due to the interaction with the sample. And if you just simply take a Fourier transform of that signal, deconvolute the input line shape, you pull out the homogeneous line shape of the quantum emitters that are in the sample, okay? And so, you know, so how does this come out mathematically in terms of if I want to look at the actual wave function of the probability density or the counting rate of at the coincidence? Again, it's straightforward to put this together. You have an input amplitude, which is F. You have a scattering amplitude, which is S. So in other words, one photon goes through the sample. And I think I have an omega 1 that's swapped on the upper term. The upper term is simply a background, which we really don't need to look at. The lower term is where all the business occurs, where you have the Fs are simply a property of the KHP crystal, and there's probably a star that's wrong. And then a term with the material sample, and then delay stage. So what we want, again, as a molecular person, I want to be able to take, here's molecule A, tell me what S is going to be. Okay, or here's a system A, what is S? And so this is ultimately a scattering problem that I can write down just in terms of like I would in any sort of molecular scattering process where I have an input wave function that I'm going to bring in from minus infinity, propagate it in with a Muller operator, different Muller, and then output it back out to infinity, projecting it out in the following way. And with this, if I take the expectation values, I get the response function as a function of frequency z, and this is the scattering matrix. Now, how this occurs with photons? So you have to be a little bit careful with photons because, you know, in the difference in molecular scattering or atomic scattering, I can always have clear asymptotic separability between the atom that's coming in the molecule or whatever target is over here. This is really an asymptotic state. If you're dealing with photons, that separability is never really difficult to maintain. You have to be very careful in doing this because of the fact that the atom or target here is always interacting with the photon field. It's never outside of interacting. Even in a vacuum, it's still interacting with the photon. So you have to dress things properly to do this right. So it's easy. It's a little bit easier to separate the asymptotic photon and the material by placing everything into a cavity and then looking at the exchange of a non-cavity photon with a cavity photon, and then everything inside the cavity can be dressed properly. So we do this And I don't think I have the slides for the, we use a technique for what's called input-output theory. So we imagine that the photons are stochastically exchanged one for one with a cavity at a given rate, and then output to the at a given rate. And the test case for all of this is the Dickey model. And the Dickey model is like one of these toy models that goes, it goes all the way back to the 50s. And it's such a subtly complex system. You have a series of spins that you can collect together in a common spin quantum number, J, and you have a photon field psi, in this case a single mode cavity, and this looks like the simplest, quite simply the simplest problem you could imagine trying to solve. It's amazingly complex, and first of all, I have it written in this non-rotating wave approximation form, which is critical. If we do this in the rotating wave approximation form, where we would only have the coupling between psi dagger and J minus and psi and J plus, where you would have a conserved number of particles in the system really doesn't undergo anything interesting other than its Rabi oscillations. If you include these non-rotating wave terms, you get really a phase transition, a symmetry breaking phase transition that leads to the effect of superradiance and non-superradiant states in the system. And it's that sort of onset of superradiance that we wanted to look at with quantum light. So what is superradiance, like I just said? If you break this down into the what's called the Jaynes-Cummings model, you have a spin interacting with a boson in the following way. Perform Holstein-Primakov on this. You can write down all of this in terms of interacting oscillators, and you get these counter-rotating terms. And it's interesting to note is that in this particular model, that the number of excitations in the system isn't conserved. So number of energy eigenstates are not number states. So n is conserved on average, and there's also a phase uncertainty in this system consequently. And if you do that, and you look at the Heisenberg dynamics of a system like this, on resonance, you wind up getting an instability whenever the coupling is on the order of the frequency. So you get this superradiant phase that occurs. One mode grows exponentially, one mode dies exponentially. And this is the onset of superradiance. And if you put a bunch of oscillators together in a cavity, you start approaching the thermodynamic limit, and you undergo a quantum phase transition. And this is a well-known effect. There's some issues with this, whether or not this is a true quantum phase transition, whether or not the system is gauge invariant, and such has been debated in the literature. For an open quantum system, those issues are not necessarily of concern because you're always pushing photons in and out of the system. And so anyway, so what we wanted to look at with this idea of quantum light is what is going on in a Dickey model system as I push it through this instability region, as I push it through the phase transition. It's a very difficult, monitoring onset of phase transitions in any kind of system is difficult and certainly spectroscopically difficult. But we wanted to see what would be something that you could get out of this. So again, let's look at what's going on if I have a Dickey model in a cavity that allows photons to leak out of the cavity. Around the onset of the phase transitions, this is plotting the lower polariton branch and its conjugate as a function of the coupling strength, which is proportional, if you want, to the number of spins that are being represented in this lattice. And so as I push through the phase transition, which at this point occurs right at where this little bubble opens up, you wind up again with this growth of one mode and a decay of another mode, and this sort of width of this phase. If I had zero cavity leakage, this point that I'm showing with cavity leakage would be exactly zero. But if I have a little bit of cavity leakage, that expands out, and so you have one mode that grows, which is these blue lines, one mode that decays as I go through this. So what's going on in that case? If I go through if I look at this, and there's the normal regime, which is your normal radiant regime, which is identical to what you would get with rotating wave approximation, and then a super radiant regime, which is something that you would not get with the rotating wave approximation. You can see that different modes of the system, different expectation values of the system grow, and some die off as I go through the super radiant transition. So you can see that the amplitude, for example, of the photon field grows. One mode of the amplitude grows as I go through the system, as I go through the super radiant transition. So what would I look at if I were to take a Dickey model and plug it through input-output theory, calculate S matrices and all that kind of stuff, and we can look through the sausage if you wish. It's in our paper that I reference here, and we get signals. We get what would be experimental signals if you could actually do this experiment. And as you go through the phase transition, you get more wiggles. Great. Okay, so what is this telling us? So okay, great, you get more wiggles. They're all in the right place, what we think it should look like. It looks like they're stretching out to farther and farther time as I go through the phase transition. Okay, I said, this is Carlos and I at Telluride, and we say, hey, great, what's going on? So you look at the Fourier transform of the signals, and really what's going on with this, if I take the Fourier transform of each one of these, I'm mapping out the poles of my scattering matrix, and hence the eigenmodes of the dynamics of this non-condensate to condensate system. And I can do this. And again, as a function of the number of emitters that we put into the system, you push yourself through this phase transition. Now, if you sort of blow this up, and if we can carefully tune the number of emitters or the coupling strength or how hard I drive the system, I start expanding out this super radiant transition a little bit, and you start seeing some really interesting and complex modal structure that's evolving as the system is undergoing a quantum phase transition from the non-radiant or the normal radiance to super radiant regime, and this really got us interested. What's going on? You have this sort of different kinds of modes that are growing at different kind of ways, and there's some very complicated many-body dynamics that are going on in the system as the system becomes very collective and undergoes this quantum phase transition. So that gave us an indication that, yeah, there's some very non-trivial information that one can extract out of a system. This is simply looking at one quantum photon going through the sample and then partnering with its pair back through a beam splitter and looking at the output signals. This is what would be the quantum spectroscopy of a single emitter undergoing or an ensemble of emitters rather undergoing quantum phase transitions. So again, looking at this in a molecular viewpoint, I want to be able to dig out, well, what's going on within the system. Dealing with toy models and spin models is fun. I can do this on the computer, or we can play around with different kind of condensates. But again, the first part of my appointments is Department of Chemistry, and so I need to think about what about chemistry can we get out of quantum light? So let's again think about what might be of interest in a chemical sense. Well, in my own area, I'm interested in how excitons interact with each other. How do excited states? What happens to molecules in their excited states? And so let's imagine that I have two chromophores, C1 and C2, and they're pegged together on maybe a biomolecule or a DNA, like Andy Marcus likes to work on, or maybe on a stretchable chromophore. And I say, well, let's imagine that those are just two uncoupled qubits, and I have a red photon and a blue photon that's interacting with this whole system. And they're coupled to each other both by hopping. There's a repulsion term that says if if both sites are excited, that the excited states have an anharmonicity that increases the energy, and I allow excitons to hop in between, and I also allow the whole system to be photoexcited. And I get an energy level structure. This is simple. You can work through. If we're dealing with molecular aggregates, we would call the lower state with negative J the bright state. A J aggregate state. We'd call the upper state my H aggregate state, which is dark. We'd have a ground state and a double excitation state. So, okay, right. What can we learn about doubly excited bi-exciton states with quantum light? So let's just look at it first of all as a cascade. Can we get anything out if I put all my excitation in the upper state and look at the 2-photon emission? This is just simply not even putting in an input state. Look at 2 photons coming out of a doubly excited system. And sure enough, yeah, this is, again, an analytical result that you can work through with non-perturbative Green's functions and calculate the outgoing photon amplitudes for a system like this. And sure enough, yes, you get this really interesting asymmetry in depending upon the kinds of interactions that you get in the system. Now, if you have an interesting case, of course, the non-interacting system is not very interesting. It's nice and symmetric. But there's also an interesting case where the intermediate level is exactly in between the upper level because the anharmonic interaction is canceled out by the hopping term, fortuitously canceled out. Then you again also wind up getting this nice and separable photons going out. But again, you can analyze the entropy of this sort of 2-photon state that comes out of the system and then say something about the nature of the interactions of the system. And again, this is it would be a relatively straightforward frequency resolved coincidence measurement. Now, excitons interact in lots and lots of different kinds of ways. They interact with their environment. They interact with the fact that their coupling is being modulated by the fact that their transition dipoles are doing this, and they're doing all sorts of kind of crazy dynamics going on. Can we pull out something about the dynamics by looking at these interactions? So again, going back to this idea that I had, well, let's imagine that I can write out the scattering matrix, which I'll write out as S, in terms of a series of interacting scattering events whereby one photon, let's say the K1 photon going out to K prime photon, interacts with one of my 2-level systems, and the other guy interacts with the other one of the 2-level systems. Of course, you don't know which one is which. But every once in a while, the 2-level systems in their excited state start talking to each other. Maybe they interact once, twice, and so on. Well, this is a problem we can solve analytically. This just gives you a geometric series in terms of this interaction. And I can always, I can always rewrite that geometric series into something that looks like this lower equation. So if I do that, I get something that looks like the following. Let's just imagine that every time these excitons interact, there's an interaction term. Let's call it squigma. Little squiggle here, and there's a phase that goes along with that. And if I simply allow that contact interaction to be a constant, just something every time I interact, I get one of these, I pick up a little psi interaction and maybe a phase, I average over the phase, and you can get, again, going from something that's nice and separable with no interaction to something that would enjoy this anti-squeezing due to the interaction. So in other words, there's a one-to-one correspondence between the degree of squeezing that I get in the 2-photon output state and the Fock state that goes out and this interaction. Analytically, one can show this. You can show this here. So this is, it's straightforward to work this through. You can show that if you do single value decomposition on these functions, you can show that the single value decomposition are related to this entanglement parameter that we impose. You can calculate an entropy. And there's a one-to-one mapping between the entanglement parameter and the entropy that one would measure by simply doing single value decomposition of this 2-photon state. You can allow the interactions to be, maybe they're random, maybe there's some noise that goes on in the system, and you phase average over the whole thing. Interestingly enough, if you have phase average scattering, again, you get this analytical form for the entropy. It's a little bit messy, but it's easy to work out. But again, there's a separability that depends upon the magnitude of the interaction and also the magnitude of the noise that's modulating the interaction. Okay. If we allow that interaction to be Gaussian, or the noise that drives the interaction to be sampled from a normal distribution, you get something different. And what was interesting in working through this, again, these are all just analytical results for the most part. You get different kind of biphoton squeezing. You get different kinds of photon states in the output depending upon the kind of noise that's driving the two excitons. So again, you're getting dynamical information by looking at a measure of the cross correlations between this exciton to this exciton by looking at the output photon state of in this kind of a system. Now, this is probably a hard experiment to do, but nonetheless, it tells me that, and maybe it's a little hard. It's easier if you look at the entropy itself. That there's a squeezing that's going on, and it's entirely due to this very weak interaction between excitons. So we push this a little bit further, and again, being somebody who likes to think about spectroscopy, whenever you think about random processes driving spectroscopic dynamics, you immediately fall back to the venerable Kubo model, which is this beautiful paper by Kubo back in the 50s or 60s, reviews of advances in chemical physics. And basically, in the Kubo model, which is what we teach in our spectroscopy class, if you have a single oscillator that has a modulated energy gap that is Gaussian, on average, that gap it averages about its Barysh transition frequency, but you have a Markov decay in the following form, that the correlations in the noise drop off exponentially in time. There's a correlation time for that and a magnitude for that. Okay, this is the heart and soul of the Kubo model, which gives us the dephasing time, homogeneous line shapes, and et cetera. If we assume that this cross correlation also has this Kubo form, we can write out any cross correlations between the one photon transition frequency and the other photon transition frequency at a different time, again, in this exponential form. We'll just postulate that that's possible to do, and that this would be the form that we would get. And you can then calculate, again, following through a Kubo-type analysis, a cross-correlator between one exciton and the other exciton. Now, the difference at this point is that you have to be very careful about when you have to be very careful time ordering, because you don't know which photon arrives first and which photon departs first. And you can sketch that out in the following way: that you have 6 possible different processes that go on or pairs of 3 processes that go on. And there's different ways you can time order this particular integral, again, depending upon which photon arrives first and which photon doesn't. And what we find, you get some expressions that are nice and complicated looking correlation times expressions. And of course, these are all up at an exponent. But rather than dealing with this, looking at these as complicated expressions, what you want to do is to look at this in the limits of when. So there's the common parameter in all of this is the magnitude of the fluctuation sigma and the time scale for that fluctuation to decay tau. If we look at this in the 2 different limits, as you would in the Kubo model, there's an inhomogeneous broadening limit where there would be no entanglement. And in the inhomogeneous broadening limit, that term is very small. Everything becomes separable. Okay, everything is separable, and the magnitude of this depends upon the timing between of the incident and outgoing photons. So when did one photon leave and when does the other one go? There's also a homogeneous broadening limit, in which case it's sort of like the system is being slowly modulated by the environment, and you're sampling all possible environments co-environments of the system, and you wind up getting entropy generation for the system. Let me just go forward. You can also do this with resonant scattering from J aggregates. It's a little bit more of a complicated expression, and in doing so, we show that you can distinguish between J aggregates versus H aggregates simply by the outgoing photon amplitude of the system. And so again, why quantum light? I think I've managed to convince at least myself, and maybe Carlos Silva, who's my collaborator, that yes, that this is very sensitive to many-body correlations. There's a lot of non-trivial correlations that one can extract from a system like this. Ultimately, one should be able to do this with CW sources rather than pulse sources. And I think this is relatively unexplored for spectroscopic probes on real molecular systems. So Carlos is trying to do this, Andy Marcus is doing this, and a few other people in chemical physics are exploring this, but it's a relatively untapped area. It's difficult, but it's untapped area. So I want to thank everybody and thank my collaborators and you all for inviting me, and let's make photons quantum again. Thank you.
Okay, time for questions? Yeah.
Can you say something about the relative magnitudes of, in that cavity superradiant limit, the relative magnitudes of, say, G, the coupling, the decay from the cavity kappa, say, and gamma, the decay of the excitons? Like, are you in like a strong coupling regime?
This is a strong coupling regime. Yeah,
it's in the strong coupling.
The superradiant regime is clearly strong coupling. Yeah, absolutely. Yeah, you can. Yeah.
Is that reasonable for the experiments? Are
you
they?
Certainly, absolutely, yes. You certainly see. The Dickey model is used as a model for Bose-Einstein condensation and systems. Yes, it's certainly reasonable. And the thing is, it's macroscopic, right? So as you build up more and more spins in the system, you push yourself into this superradiant regime.
But you also have more decay.
Oh, sure, yeah, but you know.
So are you still in the strong coupling regime when you?
Oh, sure, absolutely. Yeah.
Okay.
Yeah, absolutely.
And similarly, can you say, like, for the you were mentioning that the nonlinearities, or sorry, the in that regime of like beyond the rotating wave approximation, you presumably again you have to have G comparable to the optical frequency or something like that.
That's the criteria in the James Cummings model without RWA for the onset of superradiance. Yes, and again that G has a square root of n.
Okay,
number
so
of
that's where you're getting the.
That's where you get pushed into.
That's where you're getting the enhancement from the square root of n.
Yeah, exactly.
Not necessarily from the cavity itself.
No. I mean, the cavity sort of enhances the number of times that the photon interacts with the system.
Right.
It certainly pushes you further and further into this strong coupling regime.
Sorry, finish yours.
Yeah, but you know, still when you transform to the from individual spins to this collective J, you pull out a square root of n.
You pull out the square root of n.
Yeah.
But does that still maintain with inhomogeneous broadening with polymers or the kinds of molecules that you're studying? Does that still work out? Are all the n atoms identical in your?
Well, certainly not. And this is something that again, there is a limit at which if you have this absolutely crazy degrees of energy and homogeneity in the system, your system just, you never build up to that large macroscopic number. However, if you think about it in the sense that the wavelength of light that you're dealing with in the molecular size of the system is very small. You're really sampling over lots and lots and lots of environments. So you could almost imagine that if you have a cavity mode, you're always sampling a very narrow region of this inhomogeneously sampled system. So you can always build up a large network of polaritons. This is why in the organic systems you can get room temperature condensation, even though you would think this is a much more messy system than a semiconductor system, and because you have stronger dipole coupling between the chromophores, unless you also can sample with a single cavity mode, very large wavelengths. Yeah.
Okay, thank you.
Okay, if there are no further questions, let's thank Eric again. Okay, next we'll have Martin Head-Gordon. Martin got his PhD here in Pittsburgh at Carnegie Mellon, working with John Popel, and he's going to talk to us about work he's been doing on developments of quantum chemical methods for treating electron correlation.
Oh, all right. Holy smoke. All right. Well, enough said about the penguins. Okay, so I want to tell you today about conventional quantum chemistry, and maybe this is an appropriate topic in light of the interest in quantum information, because quantum chemistry is viewed as one of the maybe promising sort of forefront areas for application of quantum information. And to kind of think about those issues, it's appropriate to put in context what are the frontiers and what can be done and what can't be done today on classical computers. So let's see if I can get this thing to cooperate. Okay, so the electronic structure problem is easy to state and hard to solve. We firmly clamp our nuclei into position. We then simply seek the lowest eigenvalue and eigenvector of that electronic many-electron Hamiltonian that describes the quantum chemistry problem, the electronic structure problem. And of course, it's the inter-electron Coulomb potential that gives me a job, makes this problem difficult. And the wave function, the exact wave function, is therefore an entangled superposition of determinants. And that is impossible to solve exactly, but if you could, you would then have, in principle, chemically accurate potential energy surfaces on which interesting, complex, applied chemical reactions would take place, catalysis, for example. And so in the catalysis context, you could then discover mechanism. And my research, and in fact it's really in some sense been my research interest ever since I was a graduate student with John Popel, is trying to develop approximate models that are accurate enough to be useful and efficient enough to be feasible, and explore their implementation. So that's quantum chemistry in a nutshell, and my talk today will then involve two different aspects of this. One is about the design of density functionals, and then the second is about a simple wave function-based method that can overcome some of the difficulties that density functional theory still faces. So why density functional theory? Well, it is used by on the order of 100,000 chemists, material scientists, condensed matter physicists. There's easily 10 to 20 large software packages, one of which I have wasted much too much of my career on. These software packages typically involve on the order of millions of lines of code. Ours is on the order of 10 million. It takes many people to put these together. They're on the order of 300 contributors to the latest version of our code. And in some sense, you have to work in teams to get this kind of stuff done. And then you can do quite interesting, quite intricate chemistry. So this is catalysis associated with a Diels-Alder type reaction involved in the processing of green chemicals. This is a path to the chemical that's the precursor to plastic bottles. And this was work that I did in collaboration with Alex Bell and a shared student of ours, Ipe Lee, kind of showing you the way in which you can walk through a very complex, intricate reaction mechanism. And today, roughly 95% of quantum chemistry calculations are done with DFT. That's not because it's a perfect theory, it's because it's a pragmatic theory. So it has failure modes, and it's good to understand them, and yet there are good reasons why it's so widely used, and it's important to understand those as well. And really, the bottom line is 95% of chemistry is easy. The difficult problems, the ones where there are genuinely strong entanglements, it's not that they're non-existent in chemistry, but they're rare, relatively rare. Okay, so what then is density functional theory, if you're not familiar with it? Well, we seek to replace the entangled many-electron wave function by simply use of the electron density as the basic function that controls the theory. And beautiful theorems, the Hohenberg-Kohn theorems, guarantee that the ground state energy can be, in principle at least, exactly expressed as a functional of the density, thereby creating a nice challenge. The first challenge is that even today, there is no satisfactory density functional for the kinetic energy. So in fact, we use a single determinant of molecular orbitals, in other words, a wave function associated with non-interacting electrons, to represent the non-interacting kinetic energy exactly. The electron nuclear attraction and the classical Coulomb repulsion are likewise exactly represented in terms of the density, and this just leaves behind exchange and correlation as the truly quantum effects that are non-trivial to model as functionals of the density. And in my opinion, the true exchange correlation functional is essentially unknowable. In other words, we will never know it. If one is after exactness, one should go via wave functions. However, one can model it and get acceptably close. And so this part of the talk is really about what is the state of the art, in my group at least, about trying to model the functional. And obviously, we're balancing accuracy against feasibility on classical computers here. Okay, so in terms of trying to put this in some context, a very famous density functional developer, John Purdue, has introduced a useful categorization of density functionals as rungs on a metaphorical Jacob's ladder that ascends from some primordial ooze called the Hartree world, in which electrons don't even have the correct spin symmetry, and gradually ascends towards the heaven of chemical accuracy that would correspond to solving the electronic structure problem. So rung 1 is already somewhat useful, and that's the local spin density approximation, which solves the uniform electron gas problem exactly and leaves us with an exchange correlation energy density that depends only on the density in a pointwise fashion. If you're thinking about electron correlations, this is sort of a staggering thing to look at because it involves the integral over only one electron coordinate, yet it is describing exchange and correlation that are 2 and higher electron processes. Then one can advance to the generalized gradient approximation where local density gradient information is introduced. That's rung 2, and this is really the workhorse rung of condensed matter physics. And it competes these days for viability with rung 3, which is introducing essentially second derivative information as well, the so-called kinetic energy density. And at rung 4, one is then trying to introduce information that is wave function in character beyond the kinetic energy. And this is then exact exchange or a dependence explicitly on the occupied orbitals of the cone-sham determinant describing non-interacting electrons. And of course, at rung 5, approaching the heaven of chemical accuracy, one is then introducing a further dependence on the virtual orbitals. And at that level, almost anything is possible. And of course, the expense then begins to rise rather rapidly. So in some sense, this is the broad landscape of density functionals today. And it does leave out one important advance that must be mentioned, which is that much of chemistry, especially in complex systems, critically depends on dispersion. Things like colloidal behavior, self-assembly, adsorption of reactants on active sites depends on dispersion, which cannot be described as a function of the position of just one electron at all. And so it's now common to dispersion correct standard density functionals, and this is done either with an interatomic potential a la Stefan Grimmer, or alternatively as a genuinely non-local van der Waals density functional, such as VV10 or VDW DF2. These will be joint functions of 2 electron positions. And these corrections make a very dramatic difference in the accuracy of non-covalent interactions. So I'm showing you on the left a standard functional without dispersion corrections, and on the right with, and you can see the dramatic reduction in RMS error. Okay, so that's setting the stage for the development of new functionals. And to further set the stage, a challenge was issued in this science paper from 2017, where the authors stated that as a function of time, the accuracy of atomic densities became closer to exact ones, reflecting theoretical advances until the early 2000s, when this trend was reversed by unconstrained functionals, sacrificing physical rigor for the flexibility of empirical fitting. This statement's worth taking note of, which is that density functional theory is typically not a fully first principles approach to electronic structure. It's a somewhat empirical method, and then depending on how empirical you want to make it, it may simply become an exercise in data fitting. The data that they were concerned about was the electron density of a dozen spherical atoms. And on the y-axis is the RMS error in the density of the spherical atom. On the x-axis, a little strange, it's the year in which the functional was introduced. And the point was this line, which is some sort of guide to the eye, showed improvements up to the millennium and then perhaps a degradation, reflecting the danger that the authors spoke about. I would just note that all 14 of the worst post-2000 density functionals tested in that paper were actually developed by only one single research group. And so in principle, this kind of analysis is tricky. If you remove those data points, the overall trend looks actually less unpromising. This is just a reminder that anyone who gets up to speak about density functionals should be a little humble about the possibilities. But the conclusion of the article was that overall DFT is in need of new strategies for functional development. And what I'm telling you about in this part of my talk is the new strategy that our group has been following for roughly the past 6 or 7 years now. And this is what we call survival of the most transferable. And this is, in a sense, a form of supervised learning in which instead of using a limited amount of data to train the best possible functional, we use most of that limited data to test functionals, and only a small fraction, about 1/5 of it, to train functionals. By doing this, we should be able to find something that has predictive accuracy rather than simply accuracy in its domain of fitting. Ideally, we would use a nearly infinite amount of data. In practice, we are limited to about 5,000 pieces of data. And as I say, we use about 1/5 of it for training, the remaining to then take a very large number, on the order of billions typically, of candidate functionals and try and look for which ones test best on the data that we have reserved for testing. That testing process itself introduces some selection bias, so then we have to keep some secondary test data to make sure that after we select the best one, that it actually transfers to data that's reserved for secondary testing. Okay, and a lot of data, don't stare at it. The main point to say is that this covers chemical energy differences that include non-covalent interactions. So that's the NC, broken up into easy and difficult. Difficult being the systems where DFT will have a failure mode. Likewise, isomerization energies I, thermochemistry TC, and barrier heights BH. Just a quick look under the hood. What is going on here? The unknown bit, so remember everything else but EXC is exact. So here is the inexact model for EXC, and it's got, well, an unpleasant number of terms, 5 of them here. 3 of them are the one-point functions, which look like, for instance, integrals over the coordinate of 1 electron, and then an inhomogeneity correction factor written as a power series in the density gradient if we were doing things at the GGA level, or a double Taylor expansion, 2D Taylor expansion, if we're including the kinetic energy as well. And these polynomial expansions make no sense to carry to very high order, so we typically truncate them at about 4th order. And then every parameter that's contained in these linear expansions, CJK here or CJ here, can either be included or excluded from a functional. And that gives rise to a space of density functionals that we can train in and search over. And the dimension of the space is the most interesting thing then. So if we're doing the GGA type expansions here, we have 5 parameters for one expansion. We have 3 such expansions, so we have 2 to the 15th possible functionals on the order of 100,000. We can enumerate them by brute force. So this is not fashionable in machine learning where you try to avoid it, but this is the best answer you can get with a given amount of data. In the meta-GGA, it's very interesting because we then have 25 terms in a single expansion on the order of 2 to the 75th for the 3 expansions we require, or on the order of Avogadro's number of possible functionals. Of course, I cooked the numbers to give you Avogadro's number, but you get the idea, right? This is a functional genome, in my opinion. You cannot search it explicitly, and it's an open question whether or not you can machine learn in that space or not. Okay, and so that takes care of the first 3 terms. And then the last 2 are non-local corrections for exchange, so a 2-point integral, and then the 2-point integral I already mentioned for van der Waals. So the result of this, to kind of try and summarize roughly 6 or 7 years of work in one slide, is a bunch of functionals. We have trained on the order of 1 trillion functionals. We have only published 4 of them. And basically, we're stopping here because it's a little difficult to know what to do next. So each of these 4 functionals, well, the left one inhabits rung 3, the middle 2 inhabit rung 4, and the top one and the right one inhabits rung 5 of that Jacob's ladder. And they've got various characteristics. So the semi-local bit and non-local exchange, non-local correlation, we have either meta GGA or GGA. We have these no correction for non-local exchange. We always use a van der Waals density functional. And in the case of a rung 5 functional, we even have wave function type correlation in the PT2 form built in as well. The dimension of the search space and the number of parameters are interesting. So we have these giant search spaces, but in fact, we retain in the end relatively few of the parameters we could have retained. These are typically between 10 and 14 parameter functionals, and we allowed in the search process the possibility of up to nearly 150 parameters to be retained. Why are so few retained? Well, in part it's good. It means that we're building a smooth functional, and in part it's bad, which is that our form is not flexible enough to use all of the capability that we allowed it. All right, so now let's try and summarize how these things do for chemistry. Looking across our database of about 5,000 data points, we test our own 4 functionals and roughly 200 existing ones, and pull out from each rung of Jacob's ladder the best performing functional. There is only one functional at rung 1, so these are the 1 sigma errors for each of those data types I showed you before. Non-covalent interactions that are easy or difficult, isomerization energies, easy and difficult, thermochemistry, easy and difficult. To pick just one, the 1 sigma error here is 10 kilocalories per mole. If you are tough in terms of your statistics, you'd like 2 sigma or 3 sigma, this is then becoming something like 1/4, 1/3 of the chemical bond energy. It's not useful. But at rung 2, our combinatorial design could not meaningfully beat the best existing rung 2 density functional, which is in our hands for this data, the B97-D3 functional. And you can see how useful it is. It's a 3-fold reduction in RMS error for easy thermochemistry, and similar or better for non-covalent interactions. So everything gets better, nothing gets worse. You begin to see a significant difference opening up between the easy problems and the difficult ones. Again, we curated what's easy and what's difficult. We have reasons for it, but it's important to see a failure mode of DFT growing in. At rung 3, the best functional is our own combinatorially designed one, and it improves on, well, everything. No measure of statistical error gets worse. Everything gets better. At rung 4, it's our range-separated hybrid meta GGA. Again, everything improves, nothing gets worse. At rung 5, it's the same again. Everything improves, nothing gets worse. Let's take a pause and then ask ourselves, where does this stand relative to the best quantum chemistry that is done with wave functions? The answer is still significantly less accurate, maybe on the order of 5 to 10 times less accurate, at least, than the best couple cluster type methods. So this is very good, useful for a lot of chemistry, but not perfect. And I think the nicest thing about it is that the RMS error in each category decreases with each step up Jacob's ladder as represented by the best functional at each level. And in that sense, DFT is statistically improvable. If you pick just one problem and you ask what are the errors as a function of functional, it doesn't necessarily go down as you go up Jacob's ladder, but in a statistical sense, it does. Well, you may say, this looks interesting and almost impressive, but it is his data, right? So So what about someone else's data? So this is independent assessment of density functionals from Lars Gorik and Stefan Grimmer's groups. This is the so-called GMTKN55 data. And at rung 2 over here, the best well, it's hard for you to read, actually hard for me to read even. B97-D3 is the second best functional they test, so that's roughly comparable to our conclusion. At rung 3, the best functional is exactly the same as we conclude. At rung 4, the best functional is exactly the same as we conclude. And at rung 5, the best functional is the same as we conclude. So, of course, the results depend on the data. This, by the way, is main group chemistry, so it's excluding transition metals, for which it's hard to get first principles data. But nonetheless, this largely echoes the conclusions I showed you before. All right, so this looks quite successful. Caveats are you need large basis sets to actually get the accuracy that I showed this is capable of. And secondly, it doesn't actually solve the great problems of DFT. They still exist. These methods fail for the difficult problems, which are associated with self-interaction error and strong correlation. There are interesting questions about can we go further, do better in the future with broader data. I don't know the answer to this, but we're trying. Other independent descriptors to make a better functional is the critical question, and that's the end of that part, and I will now switch gears to a wave function method that we've been working on for the last couple of years called kappa OOMP2, and this is a regularized MP2 method, and I will try to explain both of these concepts to you, and this work was done by Junho Lee, a very, very wonderful student in my group who's graduating this summer. If you don't know what MP2 theory is, let's just take a moment to refresh. So we're now leaving density functional theory behind and thinking about wave function-based quantum chemistry, and the starting point is then mean field theory, Hartree-Fock theory, which is self-interaction free, that is, we do the exchange exactly, but it has no description of correlation beyond the statistics of fermionic exchange. So if we do perturbation theory, textbook basic non-degenerate quantum mechanical perturbation theory, starting from mean field, we have a zero-order problem with a zero-order eigenfunction, which is the Hartree-Fock wave function. This is the mean field Hamiltonian. This is not the Hartree-Fock energy E0, but if you take the expectation of the Hamiltonian, well, that would be the mean field Hamiltonian plus the fluctuation potential, which is the perturbation. So Hartree-Fock theory is correct to first order in this kind of perturbation analysis, this Müller-Plesset series, which is where the name MP2 comes from. And MP2 is then the second order correction, almost right out of a textbook. The first order wave function, which turns out to be a sum over all pair correlations, over all promotions of two electrons at once out of the Fermi vacuum, and you get an expression that involves then double excitations, pair excitations of, well, a matrix element squared divided by a denominator, just like you expect from second order perturbation theory. And that denominator is differences of empty orbital eigenvalues versus occupied ones, and it should worry you a little bit that it appears as the inverse here. So in other words, in interesting problems where the LUMO and the HOMO come close to each other, this denominator is going to blow up. And this theory, this MP2 theory, will not be very good. A way to say that is that this is a good theory for the atomic-like correlations that would occur between two electrons in helium, but a bad theory for pulling apart the H2 molecule to break the chemical bond, unless you break orbital symmetries. So this part of the talk is really about the role of symmetry breaking in Hartree-Fock and MP2 theory. And I want to first assert to you, and it's really true, that Hartree-Fock orbitals can exhibit large artificial symmetry breakings, and that's a result of the orbitals distorting in some way because we've neglected electron correlations. So here is the spin squared value for the phenylenyl radical, which should be 0.75. It's a doublet after all. But when you do unrestricted Hartree-Fock, you get 2.1, which says that there is substantial quartet and maybe some hextet contamination in that radical. If I take a polyene chain like this C30 chain, it should also, actually it's a polyenol radical. I should get 0.75 for the S squared value. It should be a doublet. I get 5.3. There's a whole raft of higher spin states that have mixed in to try and lower the energy associated with this limited variational trial function. So what's a cure? Well, a possible cure is to take what I showed you on the previous slide, the Hartree-Fock energy, plus this correlation energy, and use that energy function to vary the orbitals. And perhaps because that includes electron correlation, the orbital should then recover. And this has been explored for roughly a dozen years or so. And the punchline is that if you just do it, you get almost exactly what I claimed. You get very nicely cleaned up spin squared values, indicating that with the presence of correlation, the orbitals no longer have to break symmetry to minimize their energy. So that sounds good. Now let's turn from artificial symmetry breaking to another extreme, which is essential symmetry breaking. This is a theory that does not describe strong correlations. So therefore, either Hartree-Fock or MP2 or OOMP2, the orbital optimized cousin, must break symmetry. So here is the H2 molecule, and you can follow the green curve, which is the energy, and you can see that restricted Hartree-Fock, which is the red branch, goes off to a crazy asymptote because it can't describe the correlations. On the other hand, the green curve, unrestricted Hartree-Fock, goes to the correct asymptote by breaking symmetry. So it's an essential symmetry breaking in my language. And then this right scale over here is the orbital Hessian, the second derivative of the energy with respect to orbitals, the lowest eigenvalue. And what you see is it goes through 0 at a special point, the Coulson-Fisher point. And beyond that, the restricted or spin-paired solution becomes unstable, and the stable solution, which has the purple eigenvalue, is unrestricted. And so there's a Coulson-Fisher point at 1.2 angstroms. And that signals the onset of the strong correlation regime to the right of this, the relatively weakly correlated regime to the left, and eventually you get independent hydrogen atoms, well, where the entanglement can be lost with an infinitesimal perturbation. So that's Hartree-Fock theory, and that's actually good. That's symmetry breaking that we want. Here's OOMP2, and of course you only get a second to stare at this slide, but this slide should be shocking. It was shocking to me anyways, originally. Now I've got used to it. So OOMP2 does not have Coulson-Fisher points. So here is the green curve again for spin paired, then breaking away to become unrestricted, and in red is the restricted one. But actually, if you look at the eigenvalue, the purple curve, it never goes below 0. So in other words, this restricted solution is always a local minimum in the orbital Hilbert space. And there is no Coulson-Fisher point. There is simply a second solution, a second independent solution that has spin polarized orbitals, but they don't have this sort of phase transition that a Coulson-Fisher point should have. Instead, there is simply a second solution that appears for bond distances greater than 1.6 angstroms. So this is actually very bad. They're disconnected solutions. And why is this happening? Well, it's because the orbital gap is closing down, and the PT2 correction is beginning to exaggerate the effects of electron correlation. How could we try and fix that? Well, we need to regularize or modify the theory in some way, and the simplest regularization is a level shift. And unfortunately, when you look into that, and we have spent quite a while looking into it, it turns out very large values are needed. So instead, a better idea, it took us a while to come up with something really satisfactory, but a better idea is to actually have an energy-dependent regularizer that switches off the MP2 correlation when the gaps get small and leaves it unmodified when the gaps are big. And there's a parameter kappa here that controls that. And so when kappa equals 0, we actually recover Hartree-Fock theory. When kappa goes to infinity, we recover OOMP2. This will interpolate between the two existing models, and while it's not easy to do it, we have got both orbital and nuclear gradients for both the common SCF methods and some slightly exotic ones that we'll talk about soon. And you can show analytically that this switches off to identically zero the correlation contributions in the zero gap limit. So instead of diverging like they would in conventional MP2 for small gaps, these rigorously go to zero. So we can now interpolate between OOMP2, ill-behaved because it actually favors symmetry restoration unphysically, and Hartree-Fock, which may artificially break symmetry, and exploring in between should be very, very interesting indeed. The question is there a finite kappa value that defines a useful method? That's the first question, and I wanted to show you the answer is yes and give you some idea about it. So here is breaking the single CC bond in ethane, and again, this is the Hessian eigenvalue. We'd like it to go through zero to exhibit an essential symmetry breaking. Regular OOMP2 does not, but different finite kappa values do. If we do it again for ethene and ethyne, you see the same sort of behavior. And so we can recover Coulson-Fisher points with a variety of finite kappas. But which finite one should we pick, if any? Well, the first thing to say is probably between 1 and 2 is reasonable. But when you stare at it more closely, you actually want a regularization parameter of 1.5 or less in order to make the Coulson-Fisher point shorter for ethene than for ethane, and shorter for ethyne than for ethene. So we look now for something smaller than 1.5, and then we do a bit of looking at data, thermochemical data. So this is RMS error in thermochemical data as a function of regularization parameter. It has a minimum, a nice deep minimum at about 1.45 that restores the Coulson-Fisher point. That's good physically, and minimizes the thermochemical error. And in fact, it is better than both MP2 and OOMP2, not surprisingly. Well, it's a one-parameter empirical theory. Transferability tests, we go look at hydrogen abstraction reactions, and one can see that the regularized kappa OOMP2 is almost as good as OOMP2, much better than MP2. And other tests, where we've got a whole bunch of them, I don't have time to go through them, basically show this is a pretty reasonable theory. So MP2 is the simplest post-Hartree-Fock correlation model, but it suffers from Hartree-Fock's artificial symmetry breaking. We would try to cure that by OOMP2, but that must be regularized. And so the regularization, we suggest that this is the right way to think about a replacement for Hartree-Fock theory. You can optimize the orbitals with this, do everything you can do with Hartree-Fock theory, with all of the good things, the essential symmetry breakings, the simple single particle picture, and none of the bad things, no artificial symmetry breaking. It's not a quantitative method. In other words, this won't put people looking to solve the Schrodinger equation exactly out of business, but it's very interesting that we recover Coulson-Fisher points and essential symmetry breaking. And I have just a couple of minutes. I'm going to try and tell you my last story, or at least a bit of it, which is how does this play out in molecules where we're not sure whether the symmetry breaking is essential, indicating radical characters in strong entanglement, or artificial. And we're going to look at two fullerenes, C60 and C36, and we're going to consider not just restricted orbitals, but also complex restricted that break complex conjugation symmetry, well, unrestricted you know, and general that breaks SZ spin symmetry. So C60, in principle, is a stable singlet species with a large singlet triplet gap. It has all the characteristics of a closed shell singlet when you look at experimental observables. Yet, it turns out to exhibit dramatic Hartree-Fock symmetries, orbital symmetry breaking. It's RHF unstable, and we found a UHF solution much lower, and Gustavo Scazzeria's group, he'll talk later today, found another large energy lowering to obtain a complex general Hartree-Fock solution. And Gus and his group concluded the nature of the GHF solutions is consistent with the pi electron space becoming polyradical in nature. Each p orbital is effectively singly occupied. But we must ask the question, in light of what I showed you before, is that Hartree-Fock symmetry breaking essential, associated with the neglect of static or strong correlations, or is it artificial, associated with the neglect of many, many small dynamical correlations? These are qualitative concepts, but they have important consequences. So kappa OOMP2 is in principle a nice tool to investigate this, so let's try and do it. And what we'll do is consider a symmetry breaking landscape where we go all the way from Hartree-Fock theory, kappa equals 0, to OOMP2, kappa goes to infinity. And we want to look for the critical value, kappa critical, that will restore broken Hartree-Fock symmetries. And so we've got these extremes, Hartree-Fock on one side, OOMP2 on the other, and in between we have a landscape where we go from artificial and essential symmetry breaking to artificial symmetry restoration, and we believe that in the middle we should see only essential symmetry breaking. And so this kappa symmetry breaking landscape can then be applied to C60. And this is a look at the measures of spin symmetry breaking, and you see that all of these measures of spin symmetry breaking, we recover symmetry around kappa is equal to 1, which is very strong regularization, arguing that in fact this was artificial symmetry breaking, not essential symmetry breaking. This is much less than our optimized value. So kappa OOMP2 suggests that C60 is not polyradicaloid at all. You can recover symmetry, you can restore orbital symmetries with essentially a very strong regularization that admits only a bit of correlation. Okay, and then you can look at singlet triplet gaps. They're consistent. You find good agreement between restricted MP2 and kappa OOMP2. You can look at natural orbital occupation numbers. You find nothing that is significantly deviating from 0 or 2. And you find very good agreement with higher level theories. I don't have time to tell you about those, but we have methods for strong correlations that also show no strong correlation in C60. You might then cross-check against a reactive fullerene, C36. And let's do the same exercise again. And what you see is something qualitatively different, which is the general orbital symmetry breaking vanishes early, but the unrestricted, it takes incredibly weak regularization to actually restore that. So in other words, you're almost all the way out to the OOMP2 extreme when orbital symmetries are restored in C36. So this suggests that the general orbital symmetry breaking is artificial. That can be restored even with very strong regularization, but that the unrestricted symmetry breaking is essential in this molecule. In other words, C36 has strong correlation, as would have been implied by the Hartree-Fock results, and by contrast with C60, where Hartree-Fock, we think, is exhibiting artificial symmetry breaking. I'm going to skip this and stop. So I hope to have shown you that while we can't solve strong correlation problems in general, this method that I've described, kappa OOMP2, is a very nice way to separate a theory of dynamic correlation from essential correlations, and we can then get symmetry breaking in a way that is physically meaningful, and it appears to resolve the origin of the mysterious complex GHF solutions reported previously for C60, and in C36, those symmetry breakings are not removed. Okay, well, I need to thank Nabe Mardarossian, the student who did the wonderful work on functional development with me over 7 years, Junho Lee, who's been with me for the past 4 years for the work on kappa OOMP2 and the fullerenes, and I had to skip the bit about complex restricted orbitals. And thank you for your attention.
Yeah, okay. You referred to machine learning approaches essentially looking in the space of functionals. There was an effort I recall hearing about a few years ago to use machine learning methods essentially to directly construct functionals by getting various densities and then. What is the status of that? I mean, I know this is not directly your work, but I'm just.
So my sense is that the biggest successes with machine learning have been to avoid use of the density altogether and go directly from nuclear positions to ground state electronic energy. The efforts to do machine learning of density functionals using densities have been for incredibly restricted domains of applicability. So in other words, literally for, say, different geometries of a given molecule, rather than a diversity of molecules such as we do.
Martin, yeah, nice talk. Of course, I disagree that C60 is not strongly correlated. I think it is strongly correlated. I'll have a couple of slides this afternoon to prove my disagreement having an important support from calculations. I guess if I understand your regularized KOOMP2, I'm a little bit surprised because not having symmetry breaking is kind of a good thing. So you I mean, this OOMP2 thing is actually quite interesting. And when you put a kappa to make it break symmetry again, I don't like that. I think it's much better without that. You know, the exact wave function doesn't break symmetry, right?
That's correct, but this is a very poor scientist's theory of electronic structure, and it contains a description of just the atomic-like correlations. There is no good description of the bond-breaking left-right strong correlations, as you know very well. And so I would argue that MP2's false restoration of symmetry is a result of an incipient divergence. In other words, you cannot expect to get good numbers out of that symmetry-restored OOMP2 method. The numbers are in fact terrible. They diverge. So we must in fact reject the false symmetry restoration of a theory that doesn't have the physical ingredients necessary to properly restore symmetry. We're not spin projecting or anything like that. So this is just an MP2 energy functional. And the argument is that we want to allow this to have its own orbital phase transition to symmetry breaking when the electron correlations are strong enough that we can't adequately describe them with a single determinant reference, which this theory is 100% built upon. So anyway, I look forward to hearing about your C60 results, and I wanted to put this up in order to set an appropriate stage.
Yeah, so I wanted to make two comments or observations. You may not know, and many people in the room may not know, that Plesset received his bachelor's degree in physics from Pitt.
Nope.
So the second is you started off saying that about 95% of quantum chemistry calculations are DFT, and about 95% of chemistry is therefore easy. I would say that there's a selection of easy problems when you do DFT, and one cannot conclude that 95% of chemistry is easy.
Ken, I think I must potentially agree with that. There may be some selection bias involved by experienced quantum chemists, and I guess I should have recognized that.
Okay. Well, let's thank Martin again. So where do we, what you're trying to tell me is we go upstairs for lunch. That's what that signaling meant. Okay.